Good evening, everyone. Welcome to our March 31st edition of our virtual evening under the stars at George Mason University. I'm excited to have all of you here tonight. We will get going in just a few minutes. We have a chat. If you're not familiar with Zoom, you can click on the chat button in Zoom and post any questions you may have in the chat, and we are going to go ahead and mute everyone for now. And let me, please do keep yourselves muted. Let me go ahead and get the show started. So these are events that we used to have in person in the before times on alternating Wednesday evenings. Our next virtual event is going to be April 14th. We're going to have David Brown speaking to us about the Europa Clipper mission. And we did just hear that the Virginia governor has, starting tomorrow, allowed for increased capacity in events, including up to 30% capacity indoors, as well as larger events outdoors. And so we are looking forward, certainly next fall, to likely being able to hold these events back on our campus next fall. But we do have two more virtual events planned in April 14th and April 28th. And we look forward to having you back. To stay up to date on information about our events, I just encourage you to sign up for our newsletter, The Moon. And you can sign up at science.gmu.edu/observatory. We also have featured astronomers, student highlights, and space updates, both things in the night sky and what humans have been up to in the realm of space exploration. We also have a philanthropic organization, so if any of you are able to, I encourage you to make a tax-deductible donation to the observatory to support the outreach and education we do here at George Mason's Observatory. And I'd like to thank our existing patrons, including our Big Bang, Galaxy, Supernova members, as well as our new Nova, Cluster, and Star members. I'm the director, Professor Peter Plafchan, and we're joined tonight by Dr. Rob Parks, our Deputy Director, as well as Kevin and William, our Observatory graduate teaching assistants. And if you're a student here at George Mason, you can go on Mason 360 and find friends of the observatory. I hear they were also recently on the GMU subreddit, and that was a lot of fun. But Brandon Iverson is the president of our student club, Friends of the Observatory, and that's free to join on Mason 360 if you are a Mason student. We also have some of our undergraduate and graduate student tour guides here tonight, including Ashley Mertzok and the others listed. So for more information about us, our events, and what we're up to, go to our website. You can also contact us on Twitter at GMU Observatory or email us at gmuobservatory@gmail.com. So it's my pleasure tonight to introduce tonight's speaker, Dr. David Kipping from Columbia University, and I apologize, it looks like his university there got cut off. He's going to talk to us tonight about the search for life in the cosmos. I'm really excited about that topic. Dr. Kipping grew up in England and obtained his undergraduate degree in natural sciences at Cambridge University in 2007. He then went on to complete his PhD at University College in London in 2011, where his thesis developed new approaches for the discovery of extrasolar moons. Dr. Kipping then moved to Harvard University as a NASA Carl Sagan Fellow, where he launched the first observational program searching for exomoons. In 2015, he joined the faculty at Columbia University, where he now leads the Cool Worlds Lab. His research spans exoplanets to interstellar propulsion, astrostatistics to astroengineering, and of course, tonight's topic, the search for life in the cosmos. So without further ado, Dr. Kipping, the virtual floor is yours.
Thank you very much. Thanks for having me, Peter. It's a pleasure to be here. And thank you to everybody coming on tonight to listen to my talk about our place in the universe. It's always wonderful to get to share my passion for astronomy, and especially this particular question, the search for life. So I'm going to share my slides. I think, Peter, maybe you're still sharing yours.
Yeah, you should be able to interrupt it. If not, let me know.
Oh, yeah. Okay. Here we go.
There you go.
You see that all right? Excellent. So, yeah, the title of my talk is a little bit provocative, of course, and the subject I'm interested in here, it's one that, you know, why is someone who, Peter introduced me, and my background was thinking about exomoons, exoplanets, and so I got fascinated, of course, into the question of life, because in a way it's a natural endpoint as to what we're doing. Why look for planets, moons, and other worlds out there, if not to eventually ask the question, do they have life on them? It's a question that I think many of us were inspired by at some point in our lives, and still inspires me today. So what I want to do is, first off, acknowledge that we'll probably have feelings about this. This is one of those questions that I think we all have some preference as to what the answer is. For instance, it's actually very common in religious circles to really prefer the idea that we're alone, that humanity has a special place. Whereas in many of the sciences, many of my colleagues that I encounter, they tend to have the position that, well, of course, there's someone else out there. It's just a question of where and when. It's just, you know, there's not really a question of whether they exist. And that's another bias. It's just in a different direction. There is a prejudgment either way. And in a way, the universe would be more interesting, you know, if we all grew up with Star Trek and Star Wars and the idea of this galactic club that we could one day join. The universe seems a lot more interesting if that's true. And so that you know, as a product of the science fiction generation that we grew up with, I think we are influenced by that. Kind of this famous poster here that was in X-Files, one of my favorite shows growing up, I Want to Believe. And I think many of us do want to believe, but what I want to just really get across is that whenever you have those feelings in any scientific endeavor, you have a feeling, an emotion about what you want to be true. You have to listen to it. You have to pay attention to it, because it will sway you. It will affect your ability to be objective, which is ultimately the point of science, is to be objective. And rather than getting hot and upset about the result either way, we just have to really try and leave our personal biases outside. That's difficult when you're talking about a question like this, that's so existential almost. But that's what I'm going to endeavor to do today, is try to leave personal biases out, and as best I can. Of course, everyone's biased, but as best I can, I just want to provide to you, what do we really know about this question? Okay, so with that disclaimer out of the way, here's our universe. It's obviously, there's no way to take a photo of the universe. This is an artist's impression. It's far too big. And we're kind of imagining that we live in the center of this, although really any point in the universe can consider themselves to be a center. It's just merely a matter of perspective. And really this is looking out in time. So as we look out into the universe away from us, we see stars, which are nearby. We see planets very nearby, and then we look further out, we see stars. Beyond that, we see galaxies. And if we look really far out, we can see these very, very redshifted galaxies right in the end here. And then finally, you get this kind of fuzzy region, which is essentially reionization. So soon after the universe actually formed, after the Big Bang, we really can't detect light past that point due to the universe was essentially ionized, and light just couldn't pass through the universe. So as we look further and further away, we're looking further and further back in time. And so logically, the furthest out we can see is about 13 billion years into the past, which is about the age of the universe. And so you might think that means this boundary is 13 billion light years away. It's actually not, it's further than that. When we look at the observable universe, the outer edge we can see, we can determine the size must be 93 billion light years across at least. That's just the observable part that we can see. Now, why is that number bigger than 13? That always confuses people when they first see that. Well, it's just because of expansion. I mean, that light, yeah, it left, when it left its source, it was effectively 13 billion light years away. But in the meantime, the universe expanded a great deal. The universe is expanding. And so now that point is much, much further away than when it was when it emitted the light. And so that's why we know that object now must be 93 billion light years away, or actually half that, given this is the diameter that I'm talking about here. Okay, so the point of this is the universe is very big. And as I said, this is just the observable portion. Here we are right in the middle. And just because we can't see past this boundary doesn't mean, you know, like the toddler logic, my kids think this, if, you know, I can't see you, that means you can't see me. Of course, there must be something beyond that, because there's presumably stars on that boundary that also can see another observable universe around them as well. In fact, we get some handle on this based off the curvature of the universe. So you can actually measure the curvature by looking at the distribution of the cosmic microwave background radiation that was emitted shortly after the Big Bang. And it appears very, very flat as far as we can tell. In fact, it's so flat that you can use that to put a limit as to how big the universe must be as a minimum. And you'd end up with this ridiculous number of 274 billion light years. So when you're talking about, are we alone in the universe? Do you mean the observable universe? Do you mean the universe beyond that? And in fact, the universe could be infinite. And if it was infinite, then surely the answer has to be yes. With infinite space, then the answer would, of course, be infinite rolls of the dice. You'd expect it to be a success. But it's kind of silly to talk about this universe that I'm mentioning here because it's completely inaccessible to us. And even most of the observable universe is kind of silly to talk about. It's much more useful, I think, to talk about our galaxy because the finite speed of light, really. Just looking at our own galaxy, there's 200 billion stars in our galaxy, roughly. We actually don't know exactly because no one's gone through and been able to count every single star. But we think it's about 200 billion stars. If you scale it up to the entire universe, as a minimum, there'd have to be like this ridiculous number, 10 to the 24, which is like 2 septillion. It's not a number you hear often used, but a very, very large number of stars that must exist in the entire universe as a minimum. However, as I said, there's probably not too much point in getting worried about that because given the finite speed of light, which is actually rather slow, extragalactic, beyond the galaxy travel looks effectively impossible, certainly on human timescales, unless we have a warp drive. And extragalactic communication, by the same effect, is similarly impossible. I think if we're going to make contact, certainly a two-way communication, where we have sort of trade and share information in live real time, albeit with a delay, then it really has to be confined to the galaxy. So let's just pay our attention to the galaxy in what follows. So when we talk about are we alone, this is the canvas we're looking at. We live about here, fairly ordinary part, the suburbs of the galaxy, as you've probably heard before, kind of a humdrum part of the galaxy. Nothing special about where we live, really. And if we want to estimate from our little location how many civilizations might exist in the galaxy, there's a famous equation that can do just that. And it's a much misaligned equation. It's a malign equation. It's been sort of claimed it has many, many flaws, and some of those flaws are true. It's also been used a lot by scientists and claimed that the results are valid. There's lots of pros and cons to the Drake equation. I've actually spent the last week making a giant 50-minute video all about the Drake equation, so I'm pretty familiar with this. It'll be actually coming out tomorrow on my YouTube channel. So if you want to hear really, really a lot about the Drake equation, that's the place to turn. In short, the Drake equation is supposed to estimate the number of civilizations. Frank Drake put it forward. It's actually almost 60 years ago today. He put it forward in November 1961. And it has a series of terms. You've probably seen these before, but we have the current rate of star formation multiplied by the fraction of stars with planetary systems, multiplied by those that have planets capable of supporting life. How many planets per planetary system have the capability of supporting life? Multiplied by the fraction of those that spawn life, the fraction of those that develop intelligence, the fraction of those that go on to communicate, and the lifetime. We have to have a lifetime because we start out for a rate. So you have a rate multiplied by a lifetime, that's going to give us a number, and that's what n is supposed to be, a number. It's not a rate, it's not a time. So this is our conventional Drake equation, and you can have fun plugging in your own guesses for these, and it's certainly okay to guess. We actually do know some of the numbers. For instance, we know that this one is about 2 per year, about 2 stars per year, sun-like stars being formed in the Milky Way per year. The number of stars with planets, well, we actually kind of know that now. That's about 1. Pretty much all stars seem to have planetary systems around them. But then when we go beyond this, we don't know. We don't know the fraction of stars that have, or how many habitable planets there are per star. We're kind of close to that. We're getting quite close, at least to knowing how many Earth-sized planets at the right distance for liquid water. But the problem with really getting this number is that Venus and Earth are both in principle habitable planets by many definitions, but Venus is clearly a very, very different world to Earth. And so distinguishing between Venus and Earth, we really don't have any way of doing that with our current telescopes. Maybe in the near future with James Webb, we might be able to make that determination. But right now, we just can't determine this number. And of course, as you go further, it's just worse and worse. We have no idea what FL is, or FI, or FC, or L. And so if you have a situation like this, all you can do is guess these parameters. And that means that whenever someone calculates n, it is a guess. I want to be really clear about that. It is a guess. It's not an estimate. It's not a probabilistic calculation. It's in some scientific terminology. You might want to dress it up to make it look more appealing than it really is. No one knows these numbers. No one knows these numbers. And your guess is as good as mine for these numbers. So n, we simply don't know that. And I just prefer to say that because it's the most honest thing to say. And the problem is, the public is probably deceived a lot, I think, by this, because there's so many papers that come out every couple of years, maybe even less than that. We have a paper that re-estimates n in the Drake equation. There's one just last year, came up with 36. But as I've just said, like, we don't know any of those numbers, so that's just a guess. That's just someone just guessing the numbers. That's all it is, nothing more than that. And likewise, you have articles like this and New Scientist that are claiming that, top 10 evidences for alien life. Number four in the list of top evidences for alien life is people guessing numbers in the Drake equation. That's not evidence. People guessing numbers into an equation is not evidence. It's not even controversial evidence. It doesn't matter if you put controversial in it, it's still not evidence. So yeah, the Drake equation is often abused, and it's kind of problematic. Don't use that as evidence. Okay, so let's come back to this Drake equation and ask about this possibility of being alone or not in the universe. What does it take? Well, let's say we're really optimistic and we say that every star has an Earth-like planet around them. It's extremely optimistic, I think, but hey, why not for the sake of argument? Now, what we can do is we can sort of recast the Drake equation here, just in terms of number of life forms, number of living worlds. Forget the communication, forget the intelligence, forget the lifetime of the species, or the lifetime of communication, I should say. And instead, this L now becomes the lifetime of the planet. How long does the planet essentially bear life for? Which is essentially that, from on the Earth, it's basically the age of the planet itself. So we might guess something like billions of years for this, maybe 5 billion years. This is a fairly optimistic way of writing down the Drake equation, but it kind of gives us a handle as to what it might take. What might it take for us to be alone in the universe? So I'm going to rearrange this a little bit. If we evaluate these numbers, we now can, and this is an optimistic estimate, as I said, but you'd get sort of 10 to the 10 billion. And so off that basis, you'd say, well, in order for us to be alone in the galaxy, in terms of just simple life, not intelligent life, but just simple life, then you would require that FL has to be greater than 1 in 10 billion, 1 greater than 10 to the minus 10. And so that's normally the calculus that most scientists are doing in their heads. And that's usually what they're using to make statements about their optimism, because that seems like a really tiny number. And so it seems like, well, surely FL must be higher than that. Now, I don't think this is going to play because of Zoom, but I did want to advertise there are several, maybe you can just see the videos as they're speaking. And essentially these scientists here are Bill Nye, Neil deGrasse Tyson, Brian Cox. They're being asked here, do you think there's life in the universe? And they're all very optimistic. And that's of course there must be. There's so many stars, so many planets. How can there not be life in the galaxy? And this is a very, very commonly held view by lots of well-established and very respectable scientists. But I'm going to push against that a little bit, as you might expect here. The real reason why I disagree with this, I think Sean Carroll, another physicist, kind of puts this very neatly. Elon Musk tweeted this. This is again this reference here from New York Times. Not surprisingly, Elon Musk is tweeting something controversial. He said, "Oh look, there's this Drake equation calculation from 2016 that says there's trillions of alien civilizations. Isn't that great news?" And Sean Carroll, very aptly puts, well, not really, because FL, which is really what he's referring to here, could be just 10 to the minus 100 on each planet. Why not? Why can't FL be 10 to the minus 100? Why is 10 to the minus 100 any less likely than 10 to the minus 20 or 10 to the minus 10 or 10 to the minus 5? In other words, what is the probability of a probability? How do you even assess the probability of a probability? I mean, there are ways of doing this, but the point is that this is an extremely nuanced question that you're asking, and it's quite trivial to arrive at an answer of pessimism. All you have to do is just make FL be small, and we have no real reason to think that FL can't be small. Okay, so at this point, I remember I gave you that warning, you might be having some reactions. Okay, you might have some reactions like, no, he's completely wrong. FL can't be small, and I have a list of reasons as to why I think that. And I'm going to try and anticipate those. Maybe I won't anticipate all of your reasons for optimism. And so I'd like to hear that if I miss some of them. But here are some of the common reasons for optimism about FL. And I'll sort of go through these. Okay. So when we talk about FL, we are really talking about this process, abiogenesis. Abiogenesis. That means the process of non-living stuff, non-living matter, turning into living matter. And even that is a difficult thing to define. Where is that transition? NASA defines something living as something like a chemical process capable of Darwinian evolution through natural selection. Other people, Schrodinger famously has his own definition, thinking about entropy. So there's no agreed definition of what even living is, but really when we talk about abiogenesis, it is this process we're talking about. Now, what do we know? What do we know about this process? I'm not talking about theories. I'm not talking about speculation. I'm talking about empirical, observational. We know these things to be true knowledge about abiogenesis. Okay, we definitely know it happened, number one, on the Earth, or at least probably somewhere in the solar system. If you really want to be pessimistic, you could say, well, maybe it happened on Mars and it transferred to Earth. But it had to have happened at least once somewhere. There had to be somewhere where it started. So there's at least one success of abiogenesis. And off that basis, people typically lean into the Copernican Principle, which is essentially the principle of mediocrity. We're here, therefore others must be here. And so the universe is crowded. That's the typical argument. We'll talk about that argument shortly and why it's actually somewhat problematic. The second thing we know is the timing. We actually know it happened fast. It didn't take 1 billion years or 2 billion years to get going. It took a few 100 million years for life to get going once the conditions were right. And that immediately seems really convincing as a piece of evidence for optimism about FL. And we'll talk about that one as well. Number 3, what else do we know? Well, we know there's no other planets in the solar system as far as we can tell. Of course, there might be life we just can't detect yet, but as far as we can tell, there is no other life in the solar system, nor are we able to produce life in the laboratory. We've never created life from scratch. It's never happened. That doesn't mean that it's an unlikely event necessarily. It just means that that is a statement that is true, that both of those things, as far as we can tell, seem to be true. And finally, the other thing we know about abiogenesis, or kind of weakly related to abiogenesis, so it's almost the least related, is that all life on Earth is consistent with a single evolutionary ancestor. We're all related, me, bacteria, plants, trees, everything, we're all just the same thing. We all come from a common originator. And so there doesn't seem to be evidence for multiple independent branches of life spawning. That's what we know. And I would claim that's about it, what we know. Here's what is not information about abiogenesis, and it's often interpreted as such, erroneously, I would claim. Extremophiles. People often point at extremophiles. Say, well, extremophiles on Earth, like this tardigrade here, they can survive anywhere. I mean, they can survive in a volcano, in the vacuum of space, whatever. You could put these guys anywhere and they're fine. So surely that is evidence that life does great everywhere, and we should expect all kinds of worlds to be inhabited. No, that's nothing to do with abiogenesis. You're making a statement there about evolution, because tardigrades are not the product of abiogenesis. When abiogenesis happened, this thing did not appear it wasn't just a random group of chemicals that came together and made this thing here. This is a very complicated nano machine that you're looking at. There's no way that just random chemicals could come together and make something this sophisticated. This is the product of 4.5 billion years of natural selection evolution operating. This thing is extremely attuned. And even if you look at much more simple things like single cell extremophiles, which certainly exist, they too are very, very well adapted. For instance, you have cryo extremophiles, which can survive the cold, and they have antifreeze inside their cell membranes. But no one really thinks that the first life forms that emerged would have had the machinery within them to have immediately produced antifreeze within them. That's actually quite a complicated process to do. So that extremophiles can survive extreme conditions is nothing to do with abiogenesis. It really isn't. All it's saying is that evolution is very impressive and can produce things which are very adaptable. Okay, so we're not going to accept that as information about abiogenesis. Okay, number two, this is another misinformation, I would say, or I've given this a little bit more slack, but the universe has lots of organic molecules in it. You can look in dust clouds and you find organic molecules. You can find urea, amino acids in space, for instance. Comets in particular seem to have quite a lot of organic molecules within them. And so that seems encouraging. That seems encouraging for abiogenesis. But I guess it's kind of similar to thinking, well, I have lots of pieces of a car lying around in my yard because they're the building blocks of a car. Therefore, I can assign a high probability of cars naturally spontaneously forming. That's not, you can't make that logical jump. It might be true. There might be some way that the pieces of the car are magnetic and they like to snap together to create life and to create cars. That might be true. But that the building blocks exist in of itself, just that information alone does not mean that abiogenesis is a simple, easy process. In a way, it has to be true. It has to be true for organic molecules to be abundant, else we wouldn't be here to talk. There's no way abiogenesis could have even proceeded had there not have been the building blocks in the first place. So our existence is somewhat predicated upon this being true, rather than this being a piece of information that tells us that, therefore, this process must be easy. We'll hear more about that idea of predication shortly. So I don't accept this as a piece of evidence for abiogenesis either. So let's break this down. Let's take these 4 pieces of evidence I gave you. We have some optimism, maybe for the first 2, about life being common, and maybe some pessimism based off the last 2. Let me just quickly break down why. Basically, none of these actually teach us anything. So that's going to be the spoiler. So first of all, let's look at number 3, because it's kind of the easiest one to deal with. We've never produced life in laboratories. Just take that case. Yeah, that really doesn't teach us anything, because at the end of the day, we don't know what the initial conditions were on the Earth. We're kind of guessing them. And that we put chemicals in a test tube and it doesn't spontaneously produce life. I mean, at the very most, it establishes that life isn't a completely trivial process to form. That's about as far as we can go. It's clearly not so easy that it just is constantly happening with any old chemicals thrown together into a flask. But beyond that, it doesn't say much. It could still be an extremely common process if you wait 1 million years for the process to happen. So I don't think we really learn much from this. Except that, again, that the building blocks are fairly easily formed. Okay, so what about number 4 down here? All life on Earth is consistent with a single universal ancestor. Now, you might think, oh, that's evidence. That must be evidence that life is rare, surely, because otherwise there'd be multiple branches of life. And again, I would reject that, and actually Charles Darwin rejected that, because you could easily imagine that life is starting on my fingertip right now. Abiogenesis is occurring, on your shoulder. But it's just that as soon as it happens, there's so much life on the Earth right now that has evolved over billions and billions of years that it's extremely well adapted, and it just immediately outcompetes any new life that forms, or even just consumes it, just gobbles it up. So we don't really know, actually, that abiogenesis isn't occurring all the time under natural conditions. It's just that it could be happening under such a short time scale, we just never really catch them. It just gets kind of eaten up and becomes in this messy globe of this bio network that we just can't really pick out this unique signature of an independent abiogenesis event. So again, I don't really accept that as a useful piece of information, actually, in the end, for saying optimism or pessimism about FL. Let's keep going. Let's look at number 1, the Copernican Principle. Okay, we're here, therefore others are here. This is one of the most subtle ones. So this is a tough one to get your head around, but it just doesn't work at all. Doesn't work at all. Now, let me be clear, the Copernican Principle works great for lots of cases. So if I was to say to you, we have moons in the solar system, therefore by the Copernican Principle, other systems likely have moons. Well, you're probably right. Here's another one. We have dust in the solar system, therefore other solar systems probably have dust in them. Actually, we know that to be true. Yeah, that worked. So the Copernican principle works great under those cases. Where it doesn't work great, in fact it completely fails, is when it's making statements upon which our existence is predicated. It doesn't work under those cases, and I'll show you why. Okay, so let's imagine we had an urn, and in this urn I put some balls. And you don't know the color of the balls. You know that some of them are green, but other ones are black. And the black ones, if you pick a black ball, you're shot dead on the spot. We never hear from you. I'm sorry for that very grim experiment. But we're gonna, if you pick a black ball, just imagine we never hear from those people ever again. If you pick a green ball, great. So I get a list of people, you come up and you pick balls, you pick balls, you pick balls, you pick balls. And we really don't know how many people before us were killed. There could be a graveyard filled with thousands of people. There could just be one person or no people before us. All we know is that you picked a green ball and you're still here because otherwise you'd be dead. You're aware that you're still alive. So you picked a green ball from the urn. That's all you know. Okay, so now you've picked a green ball and I'm going to ask you a question. How many green balls are in the urn? How many are in the urn? And you know, given that two things must be true. One that must be true is that you picked a green ball. That must be true because we just said it. Two, had you not picked a green ball, you wouldn't be here to talk about it. Both those things must be true. And if you're thinking, I have no idea how to compute the number of green balls in that urn, you're right, because there's no way to compute the number of green balls in that urn. It is statistically impossible to infer that. There's not enough information. If it seems impossible, it is impossible. But this is what the Copernican principle is doing erroneously when it talks about existence. It talks about us emerging. Let me give you a bit more concrete. So let's just switch that urn out for the galaxy. So that galaxy, each one of these balls now becomes a world, or a star system, if you like. And we're going to pick not a green ball, but a living world. That really happened. We live on a living world. So given that we're alive, we picked a living world from the galaxy. And given that, had we not picked a living world, we wouldn't be here to talk about it. How many living worlds are in the galaxy? There's no way to tell. There's no way to tell. This is an absolute failure of the Copernican principle. But you see it being, honestly, it's really frustrating. It drives me kind of nuts, but you see it being misused in this way a lot of times. Says very clearly, the Copernican principle fundamentally doesn't work when it concerns statements upon which our existence is predicated. Absolutely does not work in those situations. Okay, so I think we don't learn anything from 1. We don't learn anything from 3. We don't learn anything from 4. Last one on the list is 2. Let's have a look at this guy quickly. What about the timing? This is interesting. Let's look at the timing. Here's the timeline of the Earth. The Earth became habitable about 4.4 billion years ago. Let's call that t equals 0 on the clock. We emerged at 4.4 billion years. When did life appear? About 0.3, pretty fast. And the Earth will become uninhabitable pretty soon, less than 1 billion years. So when the Earth became habitable, we normally consider this when essentially there's oceans. We see evidence from mineral deposits that the oceans formed by this point. I think when you have liquid water, it's game on for life. When it comes to life itself, this evidence is a little bit tentative. It's actually based off the ratio of carbon-13 to carbon-12. Life preferentially picks up carbon-12 over carbon-13 because it's just slightly lighter, it's easier to work with. And so that misalignment of the natural ratio has been used in these 4.1 billion year old zircon deposits to claim as evidence for life. It's pretty controversial though, to be honest with you. The most solid evidence that comes from fossils, that's pretty direct. Then you're seeing fossilized microfossils, you know there's something really alive there. Now looking at Earth, I mean, you could say, well, what about intelligent life? How do you define that? I mean, was that when hominids emerged, Homo sapiens emerged? How do you define that? It doesn't really matter. You can push this number about quite a bit in terms of millions of years, but this is, I mean, if I change this by 1 million years, it's going to become 4.399 on this scale. It's really not going to do much. And finally, the thing that's kind of striking is the Earth becomes uninhabitable quite soon. And this is really important. And this isn't because the sun gobbles us up, doesn't enter its giant phase and swallow us. It's just slowly warming, and actually it will tip us over the edge, and basically the long carbon cycle will cease at this point. So that's that'll basically be the end for life in less than 1 billion years. Okay, so what does this mean? Look, this is how long it took intelligent life to evolve on the Earth. It took this giant swath of 4.1 billion years. What if that is the minimum time? What if that is the minimum time for intelligence to evolve? Well, if that's true, and we're here, then life kind of has to happen by this point, by 1.2, no later than 1.2, else there simply wouldn't be time for intelligent life to evolve before the death day of the Earth. Okay, so life has to start early for us to exist. So if this statement is true, if that statement is true, the minimum time for intelligence to evolve is typically many, many billions of years, then the fact that life started early isn't actually that interesting. So I'm going to put this very clearly. If the minimum time needed for intelligence is greater than or equal to how long it took on the Earth, in our case, then life starting quick is actually a requirement to our existence. We wouldn't be here to talk about had that not happened. And so life's quick start isn't actually interesting. It's not useful information. It's a necessity to our existence, it's not speaking to us about how easy or hard abiogenesis is. But that's just one assumption. Let's take another assumption. The minimum time is like this, much, much faster time scale, maybe just less than 1 billion years. Well, in that case, well, first of all, that would be pretty surprising because that didn't happen on the Earth, right? It took 4 billion years on the Earth. So if this is typical, that makes us like the weird slow coaches of the universe. But, you know, so it's already kind of in tension, but let's just consider it. That would mean that life could actually get going as late as basically now and still have time to develop intelligent life. Still have plenty of time to develop intelligent life. And so on that basis, life doesn't have to start early. It could start anytime. There's no reason, there's no requirement for life to start early. And so in that case, the actual quick start to life that we observe would be interesting because life doesn't have to start early. The fact that it does is telling us something interesting about life. Essentially, if the minimum time needed for intelligence is much less to compare to what we had before on the bottom, this is the new one, on the top, much less than how long it took on the Earth, then this would actually be interesting and we might be optimists. However, as we've already said, this is somewhat inconsistent with Earth's history because clearly it took us 4 billion years to evolve. So that's maybe telling us something. It seems odd that the typical number is 1 billion years, but in our case, it took many, many times longer than that. So it's not ruled out, but it's just somewhat in tension with what we observe. So you put this all together, you end up with very flaky odds. I read a paper about this last year, and it basically finds very, very soft odds, 3 to 1. I mean, you wouldn't bet your house on 3 to 1 odds that life would indeed start quickly again if it were given the chance to. But that's really very ambiguous. It's almost 1 to 1, and 1 to 1 basically means you know nothing. So we know a little bit more than nothing, but this is very, very soft nudge towards optimism. So altogether, we have teaches us nothing, teaches very little, and again, pretty much teaches us very little. So all of these facts that we know about abiogenesis, they basically leave us in the dark. We just don't know much about this problem, which is unfortunate. I wish we knew more. So when you ask this question, you know, does the galaxy have life in it? My answer, and I think it is the right answer, is we don't know. And that's it. And we shouldn't be scared of saying that as scientists. We shouldn't be scared of saying we don't know the answer. And the answer is not, oh, that it must be because there's so many stars, because there's no evidence to support that position. There's just no evidence to support that position. And this is where those feelings are going to come in, you know, that I want to be in a galactic federation, so this riles me the wrong way. And I'm not saying, you know, to be very clear, I think a lot of people think that I'm a pessimist and I'm claiming there's no life in the galaxy. I'm absolutely not claiming that, nor am I claiming there definitely is life in the galaxy. I'm claiming we don't know the answer. And I don't think that's a controversial position to say we don't know, because we really don't know. But in order to be open to the possibility, you have to permit both to go through the door. So I think I might just, because I want to have time for questions, I might just, if you give me a chance, I'm going to slip ahead to my sort of final slides here. because there's a few last things I just wanted to point out. Okay, if I can just, yeah, here we go. So that seems pessimistic. I want to give you something a little bit more optimistic. I should reshare my screen. Let's look back at the Drake equation one last time. We have all these numbers that we know at the beginning, but most of them we don't know. And I'm going to just forget the communication part, just forget communication. Let's just talk about intelligent civilizations, get rid of the FC. And I want to point out that this n in Drake's equation is now. That's really important. It's now. How many are in the galaxy today, living in the universe right now? Okay. And we can plug numbers into that, and we basically have this 2, and then all the constants that we really don't know too well. But again, that's now. But what about ever? If we added up all of them who've ever lived in the entire galactic history. So I'm going to give that a big sum, capital sigma symbol. So then it'd just be the number of stars multiplied by basically those same terms again. So this is the number of that have ever lived. And if I plug in the number of stars, we know that's 200 billion. Okay. Sorry for the transitions, give me some trouble here. And then what I could do is I could take the ratio of these two. So how many have ever lived versus how many living now? And we just plug in, and I'm keeping everything as agnostic as I can. I'm not choosing numbers for these controversial terms. I'm just leaving them in there. But you can see they all basically cancel out now. So if we do the cancellation, that's what we have. We have the number of civilizations which have ever lived divided by the number which are currently living is 10 to the 11 divided by the lifetime of these civilizations. We don't know L. I can't tell you what L is. It could be 1,000 years. It could be 1,000,000 years. But even if it's 1,000,000 years, that still means there's a lot more that lived in the past that aren't around anymore than are living right now. And so this has kind of been guiding my philosophy a bit with SETI, the Search for Life in the Universe recently. I want to share it with you that we have to be open to the possibility that we're not alone. We might not be alone in the galaxy, but that life might be separated from us, not through space, but also through time. So we're not alone, but they're just in a space-time sense, they're separated in both dimensions from us. It's not that they don't exist or they never existed. They may indeed exist. I think it's much more feasible that there are, of course, by that ratio, that are past civilizations than current ones. But then that raises some challenges because how do we communicate? How do you communicate? How do you learn anything from a dead civilization? And it's not impossible. So this is my final slide I just want to leave you with. These two possibilities, are we alone? What if we're alone? What if we're not? First off the bat, hopefully I've convinced you, we simply don't know the answer. If nothing else, I have to push on that because I feel like the scientific discourse has gone too far the other way. And so I'm being a little bit pushy on that just to try and rebalance things a little bit. We do not know the answer to this question. Okay, what if we're not alone though? So there's other civilizations out there. Okay, well that would mean the nearest civilization, first off, is most likely inevitably much further away than the nearest simple life planet. So the closest planet to us with life on it probably doesn't have a civilization. It's probably just simple life. Just by virtue of the fact you have more terms to go through. Okay, that's the first thing we could probably reasonably establish. The second thing we could probably say is that our civilization lifetime is plausibly much shorter than the age of the galaxy's age. I think many people would say it's comparable to the 10 billion year history of the galaxy. And so that really opens the door up for ancient civilizations. Civilizations, I don't mean extinct ones, I mean ones that are just very, very long lived. What does a 1,000,000 year civilization look like? What does a 1,000,000,000 year civilization look like? We don't know how to even pose reasonable answers to those questions, but I think it is something we should think about because they may be our best chances of actually detecting something. And finally, why, if we're not alone, why don't we see evidence for this? Because we've been looking, we don't see evidence for engineered stars, we don't see evidence for engineered galaxies or radio signals, no colonization. And so that's the Fermi Paradox. We have to understand this. There's something odd going on. If we really aren't alone, there's some refined parameter space that implies about the activities of these civilizations. What if we're alone? Some consequences here. Well, first off, it means we're really special, or not special, but somewhat unusual. And it means we should probably look after our planet. Like, it gives us an extra responsibility to look after the pale blue dot, I think. And it kind of raises questions. I've heard scientists ask these questions. If that was true, it's very hard to establish that was true. But if we could establish that were true, would that mean we'd have the responsibility to spread life across the galaxy? In a way, that's kind of a selfish thing to do, right? Because you're saying, well, I think life is special, but the universe doesn't really necessarily care about life. It's just another chemical process from the universe's perspective. So do we even have the right to spread seed across the galaxy like that? It also means, I think, even if we are alone in the galaxy right now, as I've just said, I think it's still likely, or much, much more likely, that there are extinct civilizations and extant civilizations. And so how do we seek their artifacts? And then finally, as a thought I've been thinking about a lot recently, to leave you with, how do we preserve some record of us? Let's assume this is all, this is true, that there's no civilizations which are simultaneous to us, but civilizations do crop up through time in the galaxy. Then how are we going to be remembered to the next civilization which emerges, hundreds of light years away? They're going to, maybe if they're very advanced, they could come even visit the Earth, or maybe they'll detect a beacon from us. How do we preserve some memory? Is there going to be any memory that we even existed? And that's really going to think about like time capsules. So for example, the moon is kind of one of the most pristine places in the solar system where you might think about leaving something, right? It has no geology, it has no atmosphere. It's a very undisturbed environment. If you put something a few meters below the soil on the lunar surface, that's basically going to be preserved until the sun engulfs it. And so you might think about, should this be something we should do as a record for our achievements, what little achievements there may be of our existence? And so this may be a kind of a swan song, sad note to leave on, but I think it is an important thing to bear in mind that it may not be our fate to spread between the stars, but we don't have to be forgotten all the same. So thank you with that, and I'll take questions.
Peter? He might have.
I was going to ask you to do it. I guess you didn't hear my message, Dr. Parks.
No, I didn't, but I would be happy to.
Yeah, thank you, Dr. Parks. That was a wonderful talk. Sorry, Dr. Kipping, that was a wonderful talk. But I'm going to turn over the Q&A to Dr. Parks tonight.
Thank you, Dr. Kipping. David, that was an excellent talk. I was been fascinated by this subject. And so, yeah, if people want to give their appreciation in the chat, that would be nice. But I guess the first question I have for you is more just a get to know you kind of question. I notice you have a guitar in the background. So I'm assuming you play?
Yeah, of course. Yeah, I do play, but you have to pay extra for that, Rob.
It's just what I find to be curious is among the community, musicians seem to be more common among astronomers than I find in public at large, and I don't know if you've found that to be true as well.
Yeah, I mean, I think there is a creative flair that you need in science, and obviously that can be expressed in multiple ways, including music. The other thing I've always noticed is an appreciation of nature amongst scientists. And we've come to this at the demo group meeting. We know so many scientists that love to hike or love to bird watch or love to do something with nature in the outdoors. And I think scientists both have the creative aspects and the expression they have, but they also have this interest in just observing nature as well. So yeah, I mean, I'm sure there's always exceptions either way. I'm sure some people that hate playing music but are brilliant scientists, but yeah, maybe there are some trends there.
Oh, all right. One of the things that I've recently I'm finishing reading Light of the Stars by Adam Frank. I don't know if you're familiar with his work or his
yeah,
ideas.
we've chatted quite a bit about some of these questions I mentioned. Yeah,
I would figure, considering the subject matter that he writes on. So in the Light of Stars, one of his answers, as it were, to the Fermi Paradox is essentially climate change. He makes the assertion that climate change is unavoidable. Like he wants to divorce himself from trying to hypothesize about alien societies, but he makes the claim that essentially all that burning fossil fuels there's no way around it. And so I was wondering if you could speak on that idea.
It's a really interesting hypothesis. I think even going beyond just talking about fossil fuels or climate change is just sustainability, to make it even more broad than just what we're doing to the atmosphere. There's many other ways in which the way civilizations emerge is not particularly sustainable to the environments around them. And of course, there's many examples of civilizations which have collapsed as a result of that. I mean, if you go to Easter Island, right, there's a collapsed civilization there, and it wasn't because of climate change, or at least in the sense that we normally talk about climate change, but in a way they did change their environment. They chopped down all the trees, and then the wind blew the soil, thinned it down, and it made agriculture very difficult. And so you ended up with civilization collapse in a different way. So certainly sustainability is going to be a big challenge for all civilizations. Whether we're just the dumb civilization that doesn't think ahead more, or, I mean, it's somewhat dependent on your lifetime. I mean, if individuals lived for thousands of years, we'd probably have a longer term view of this and care about sustainability more. If you live for 20 years, 30 years, that's the typical lifetime. It's much shorter than the time scale in which you're affecting the planet, which is kind of true in our case. People tend not to care about it that much. So it might be dependent on how long these entities on different planets actually exist for, compared to the timescales at which they're forcing their planets. And of course, we really have no way of estimating that. And so I wouldn't want to, I'd remain agnostic about that hypothesis. It might be true in some cases. I'm a little bit skeptical that you could put it as a blanket statement, as an explanation for everything though.
Okay. So there has been some controversy surrounding sort of intelligent life due to Oumuamua, certain claims that have been made that that was in fact some kind of scouting vessel, potentially some kind of alien scouting vessel. What I'm curious about are the sort of adjacent claims that the overall scientific community or overall astronomical community is actually resistant to the idea that extraterrestrial life exists. And I was wondering what your thoughts on that.
Yeah, I mean, it's an interesting discussion, and yeah, in a way, this discussion has happened in the past as well, or at least we've had examples similar to this happen in the past. I did a video about this on my channel recently, and I was thinking there about the Martian canals and Percival Lowell. And you know, thinking changes over time. So you look in the Victorian times, everyone thought life was common. It was like, well, of course, life is everywhere. Mars has life, the moon has life, obvious. Even though, of course, there was no evidence for it. But you know, they interpreted the Maria to be oceans, the structure, you know, the lines on Mars. They thought they were canals. So, you know, that was just common thinking. And then later on, it shifted the other way. The die went the other way, and everyone was like, oh, you know, there's no life in the universe. We're very, very skeptical. And I think these days it tends to actually be, in terms of addressing your question directly there, I think actually most of my colleagues I know are pretty optimistic. Okay. And actually think my position is a little bit silly when I talk about it. They actually tend to think my position's like extreme almost. My position is we don't know. And many of my colleagues are, how can that, surely that there must be, hopefully I've convinced you, we really don't know. And so I think most of the community is actually very optimistic about the possibility of life in the universe, is very open to that possibility. I just think it's the evidence. I mean, visitation is a very different thing to saying there's life in the universe or life in the galaxy. That someone has built a vessel to come fly by, not even orbit or hang around very long, or even get very close. I mean, it wasn't that close. It was about 0.6 AU or something. It was like 5 times further than the moon was from us. It's very difficult to take a good photo from that distance. So, you know, you look at those things, you look at that as tumbling. In that particular instance, I don't think it made a particularly good case that this really was a visitation, in my opinion, and many of my colleagues. But at the end of the day, it's not a wild idea that the universe and the galaxy could have life in it, because I said we don't know the answer to that. And maybe one of the activities is indeed to send lots and lots of probes out. I'd be a little bit surprised if the probes look like Oumuamua personally. but it doesn't kind of align. But then we really don't know what these probes look like. So I'm open to the possibility, but I do think the evidence in that case was pretty weak, and certainly not enough to convince me personally. But hey, looking for artifacts in the solar system, I'm all for that. We should do that because someone 3 billion years ago could look at the Earth and said, that's going to have a good chance of developing something interesting in a few billion years. We should maybe leave something here for them to find. I could believe that as a viable hypothesis. And so I think it would be worthwhile to look for it in the same way that we look for radio signals.
It's an interesting idea. I hadn't really thought about that one. Yeah, I used to joke that Oumuamua was in fact the scout ship, and then the comet that came by the next year, the interstellar comet came by the next year, was the mothership following up on those observations, and then the whole thing kind of took off from there. But there was actually kind of going along these lines, there was a question by William. What would you consider to be good evidence for alien life?
Well, I guess you have to define whether you mean simple life or intelligent life. Now, maybe is there more to that question, or is it just sort of left up to me to?
So either one.
Okay. I mean, this is actually a really good question because we really don't know how to do the first, to be honest with you, unless we find it in the solar system. If we find simple life in the solar system, we can imagine scooping it up, bringing it back to the labs, and having that unambiguous slam dunk detection that this really is something that was living. If you see a biosignature around an exoplanet many, many light years away, which is what really we're looking for when we build these next generation telescopes, there is a lot of worries in the community that's ambiguous. If you detect oxygen on another planet, how do you know for sure that means there's life and not some geological process which is producing it? And for instance, photolysis produces oxygen. It dissociates hydrogen dioxide, dihydrogen oxide, water, into the oxygen. And so the hydrogen often escapes and it leaves an abundance of oxygen left in the upper atmosphere. And so you might mistake that as a biosignature. So simple life, I don't think beyond the solar system I have a good answer for that. We really don't know. Maybe in a statistical sense we might be able to answer that. We just keep finding lots and lots of oxygen signals everywhere. Maybe that might build up faith that there really is something going on. In terms of intelligent life, for me that's more simple to answer. If you get a sequence of prime numbers, you're done. There's no way the universe does that naturally. So that's really the appeal of technosignatures, that they can have these like very slam dunk, unambiguous detections. Of course, if you're looking for artifacts, such as an artifact is very weak, something like just a little bit excess heat, that planet's a little bit hotter than it should be, looks like climate change happened there, that would be a soft piece of evidence to claim intelligent life. But if you set a radio signal or a laser communication, or a physical artifact, a piece of technology in the solar system, then I think you have a really strong, almost unambiguous case of intelligent life.
Okay. Yeah, my own personal feeling is, and I do applaud your bravery, as it were, to say that we really don't know too much about this subject. And I think that that sort of honestly needs to be more in the forefront of science. But I think in this case, my personal feeling is it's not just a single piece of evidence, but obviously a bulk, a library of evidence that needs to be accumulated in order to answer that sort of question. Yeah,
I mean, the danger is, I mean, it depends on the evidence you're talking about. But again, I'm just going to use the Percival Lowell as an example here, because his evidence for canals wasn't in isolation. He also looked at, if you look at photos of Mars, you see a little bit of blue near the poles. And he thought that was water. It's actually just refraction through the atmosphere. But he saw what he thought was evidence for liquid water. He saw what he thought was seasonal variations on the planet, due to which he interpreted to be vegetation coming and going, like spring and fall, which ended up being basically changes in the viewing conditions, the observing conditions of Mars. And then on top of that, he had these line structures. So from his perspective, it wasn't a single piece of evidence either. He had, in his perspective, like 3 lines of evidence. But the problem is he came at it, before he even started the study, he was well known for being an extreme optimist about life in the universe. And he even built Lowell Observatory pretty much to pursue that exact hypothesis that he felt convinced almost from day one there was something going on with Mars. And so he had skin in the game. And all of us have skin in the game. Me, you, all of us do. We all have internal biases. And so we have to be careful not to cherry pick piece of information and build a story in our mind that tells us, oh, therefore I can believe this to be true. Now, you can go too far. Obviously, you can be overly skeptical and just like rigid, refuse to see something staring you right in the face. But I do think there is a lot of, with this question in particular, the question of life in the universe, there's a lot of psychology and bias that goes into it. And we really need to be very, very cautious and self-aware of how our brain can play tricks with us.
Extraordinary claims require extraordinary evidence, that sort of thing. So another question that we have in the chat is, what other information will we need to make this a more optimistic outlook? Studying exoplanets further, SETI quote unquote results, and also if we discovered microbial life elsewhere, what would that, how would that impact our probability equations?
We discovered microbial life elsewhere, and we could prove it was independent. You have to prove that as well. So if we detect life on Mars, for instance, it can't just be our cousin. It can't be a piece of bacteria that was knocked off the Earth, or vice versa, and survived. There's some common relationship. It's an independent star, and you can establish that. Then I think there's no ambiguity anymore. You basically solved it. If you have two independent examples, because our existence is not predicated on Mars having life on it. We're not here because, or not because Mars has life. It's nothing to do with us. So if we detect life on Mars, that's a fair, unbiased measurement. And so then we're done. We know that actually you can then use the Copernican Principle. It would be fair to use the Copernican Principle then, because our existence isn't predicated upon it. And so we could extend to the whole galaxy. So yeah, I'd have a lot of confidence there was life in the universe. If we set life somewhere else in the solar system, we could establish that. How do we make things go forward? Well, we are building telescopes to try and take these biosignatures. As I said, there is some ambiguity about the interpretation, but there's lots of very smart people working on that problem very hard. And so I'm optimistic that we'll find, especially in a statistical sense, ways to tackle that problem. But hey, look, the dream, I'm a Star Trek nerd, the dream is to actually go to these places one day. And if you do that, you can answer questions that we can't imagine answering in other ways. There was a paper by Jean Schneider about 10 years ago, and he said, what's like the far limits of what a telescope can do? And he was imagining that if you had a telescope like the size of the sun, you might be able to image a continent. You might be able to image maybe a small city, but you can't image beings on this, no matter how big your telescope is. You can't watch what they're doing. You can't have that slam dunk proof of watching something crawl along the surface and see individual trees and things like this. So visitation is, people get scared of that word a little bit, but if we're really serious about answering this question about our place in the universe, it's going to at some point be a part of the story.
Interesting. Yeah, that opens the door up to a whole new conversation as to how it would be possible to actually visit these worlds, or does our understanding of physical laws need to change in order for us to break that speed limit, or colony ships or robotics or what have you. But for sake of time, let me move on with the other questions in the chat. I think you've already sort of addressed this, but the question is, would the discovery of a single alien civilization materially change the outlook of the Drake equation? 2 data points is still not that great for estimating the life in the galaxy.
Yeah, I'd say the same thing. I guess it depends. Is it current? If it wasn't current, it'd still be a big data point. If it was extinct rather than extant. But if you had a data point elsewhere in the galaxy, the real point is not that you've gone from 1 to 2. Because you're right, going from 1 to 2 seems like an insignificant change. But really, you've gone from 0 to 1. Because the one data point you're looking at with us isn't a data point, because we're only here because that happened. So I've said this already, but our existence is predicated upon that. It has to be true, else we wouldn't be here to talk about it. But this other civilization you're detecting, that doesn't have to be so for us to be here. So that is genuinely very interesting that it is so. And you can learn a lot even off that one data point. And one data point is information. 0 data points is no information, 1 data point of information. So you can learn actually quite a bit from that.
All right. Another question from Kent is, has any scientist ever substituted alternate values for the Drake equation to compensate for its mistakes? I'm going to put my own sort of spin on that, and I guess my sort of interpretation of that is how are errors, I suppose, error bars associated with the Drake equation?
Oh yeah, that's a good. I mean, error bars are definitely something people often complain about. I have to say, if you're interested in this question, I have to advertise my YouTube videos, because I'm going to have a whole thing all about that exact point. The exact point is the part 2 of my 2-parter coming out tomorrow. And yeah, I actually wrote a paper I didn't talk about today that actually suggests a better formalism, I think. Really, a lot of the criticisms of the Drake equation are about its arbitrary choice of parameters. I mean, why FL? Why FI? Why not split FI up into all the evolutionary stages? Or why not split the number of planets into, like, including moons and things like this? So there's sort of an arbitrary choice. And actually the construction of it is very anthropocentric. It's really a story of how we arrived. But what if there's a completely separate pathway that's just the Drake equation doesn't know anything about? You'd have to add that onto it. And so all the criticisms, a lot of the criticism, not all of them, but a lot of them stem from the fact really the Drake equation is more complicated than it needs to be. You're saying, I don't know something, N, and you're splitting up into 7 things you basically don't know. And so is it really necessary to split something up into 7 things you don't know when you don't know the first thing in the first place? So yeah, I check out the video, but basically the short answer is I suggest just think about birth and death. That's all. That's the only 2 things that matter. Civilizations die and they're born, and there's those 2 rates, and they're in balance with each other, and that's all that matters. The death, we're kind of in that process right now. Whether we survive or last climate change and the other challenges we face, that's the death feature. And how often are civilizations emerging in the galaxy? That balance perfectly describes how many currently exist. So I recommend you check that out. Excellent.
I certainly will. The last question we have in the chat so far is, and I think this will be the last question, and then we'll move on to the telescope portion of the evening, is from Terry, and actually is one of the sort of solutions, as it were, to the Fermi paradox, which is, could a distant civilization just not want to communicate with other civilizations, kind of like the prime directive? Like that, the last part's mine, but my part of that. But
yeah. I mean, I guess the prime directive has also been cast as the zoo hypothesis sometimes, which is the idea that we're sort of being watched. They know we're here, they're just watching us, and they're deliberately leaving us alone. There's some interesting work on that basically shows the zoo hypothesis is very difficult to maintain, mostly because the finite speed of light. The galaxy is big, finite speed of light is slow, and so it's really difficult if a new civilization emerges on another side of the galaxy. They don't know about this prime directive, so they could accidentally communicate with you. So it's actually very difficult to coordinate everybody to not interfere like this. There's a paper by Duncan Forgan that explores this with a kind of galactic model. It's quite interesting. But really, the explanation is right. You could just set FC to be 0. And what if it's not a prime directive, but just choice? They're just xenophobes. They don't want to talk to anybody. And that's not so crazy. It's not even an issue of choice. It's like, what's the point? Like, we don't spend time talking to ants in the street, right? Because what do we learn from that ant? And so if they're so different from us, there's just nothing interesting that they could possibly learn from our minds, except for studying us as an anthropological experiment. That'd be the only interest to them, but not in terms of 2-way communication. In the same way, we're not interested in ants 2-way communication, but we do study them. We put them in ant farms and watch them crawl around. And so if that's the level that they're interested in us, then you're right, there'd be no interest. So I think that's a very viable explanation to the Fermi paradox.
Excellent. At this point, like I said, I think we'll transition to the telescope portion of our evening. So thank you, David, for such a great talk. We've linked both the Cool Worlds website and your YouTube channel in the chat. I highly recommend everyone go check those out. Again, I certainly will. So yeah, if people could express your appreciation in the chat for Dr. Kipping. Thank you very much for spending your evening with us.
My great pleasure. Thank you so much for all hanging on and the great questions there. I always enjoy talking about this subject. So thanks again for having me.
Thank you. Hopefully we can do this again. All right, William, I think you're up for.
Yeah, absolutely. So thank you again, Dr. Kipping, and thank you, Dr. Parks, for taking care of the Q&A. So at this point, we'll go ahead and move over to the virtual tour of our observatory. So let me go ahead and share my screen. Okay. So right now you are looking at a desktop. It's a computer that is at our observatory. So this is the computer that we use to control the telescope and all of the other equipment that we have at the observatory. And what's nice about this is that I can observe and control everything from the comfort of my own home. And one of the things that makes that possible is that we have a series of webcams at the observatory that let us keep tabs on things and make sure things are not going horribly wrong. So if I pull up those cameras, what we have here, well, there's our big telescope. We'll get to that in just a moment. Let me just, oh, come on. It's being a bit laggy. I'm trying to change the camera view. Okay, there we go. Okay, but anyways, we have three cameras at the observatory. The fourth one that says no signal, that's in a box, so we don't expect anything. But this is the control room. It's where we would normally operate the telescope from. We are currently connected to this computer right here. And we also have a backup computer right here where we test updates and upgrades and all that sort of good stuff. So it's a somewhat small room, fairly cozy, but yeah, that is where we would normally operate the telescope from. And over here, we have an outside view of the dome. So our telescope is inside this building. Here is a doorway for scale. It's about 6.5 feet tall. And as you can see, it's currently very overcast. So unfortunately, we're not going to be able to show you anything live tonight, but we do have some images that we have taken beforehand that we can show you. And one of the nice things is that we can actually show you some processed images that look a fair bit better than the raw black and white images that we would take live. So if we go to the last camera, we have our telescope in here, and Ashley can tell you all about our telescope.
Thanks, Will. So yeah, this is our observatory telescope. It is a reflector telescope as opposed to a refraction telescope. That means that instead of lenses, we use mirrors, which tends to be better for just the general size and mobility of the telescope. You can see here in this image, the primary mirror sits in the back. It's 32 inches. That's also the aperture of the telescope. And then the mirror up front is the secondary mirror. It's about 1 foot in diameter. To understand kind of how light travels through our telescope, this dome around the telescope really protects it for weather and whatnot. But there is a door that opens and closes when the weather is nice. Unfortunately, it's not tonight, but when it is open, light will travel through the door towards the telescope and hit the primary mirror in the back. Then it will bounce up to the secondary mirror and then down to that little hole you see in the middle of the primary mirror. That primary mirror is, that little hole in the primary mirror is actually where that light is split into 4 different portals where we have instruments to detect that light and process it however we need to. So we have 4 different instruments. I'm not going to show them to you tonight, but we have a eyepiece that we would look through if we were all there tonight. Everybody'd get a chance to look through it. That is generally what people look through when they are at the telescope. We also have a Ccd imaging camera that is actually 4096 by 4096 pixels, which is a lot of pixels. So it can catch a wide view of the night sky in a frame. And we'll see one of the pictures that was taken, I think, a week ago tonight in a couple minutes. But it takes a pretty good pictures. It really takes better pictures of objects that are far away. Sometimes we have issues with viewing planets just because they're so close and so bright, and telescopes kind of act like these light buckets that collect all this light. And sometimes it can be too much and oversaturate the image. But fortunately, I think we have some good images that were processed really well that you guys can see just how good the telescope can take certain images. We also have a filter wheel. So the CCD camera only takes images in black and white, but if you wanted to take an image of light other than visible, like what we would see, such as infrared, H alpha, which is a really red wavelength, red light, blue light, we have a filter that kind of switches between those different filters so that we can take an image in each filter. We can actually assign those filters colors and stack them on top of each other to create a color image. So that is our main instruments that we have. If you have any more questions about the telescope or the instruments, definitely drop it in the chat and we'll answer what we can. But I'm going to go ahead and park the telescope so that you guys can see it move a little bit. And I'll explain this too as it is moving. So this is actually our SkyX program. It allows us to move the telescope. You can see this yellow dot is where the telescope is going. The red dot tends to be the target where we want the telescope to go, but since I parked it, it'll automatically go to a specific spot. I'm going to go ahead and open the picture. And you can see the telescope move, and you will also see the dome move around it to kind of stick with it. So like if you're observing one thing on one part of the sky and you move the telescope over to the other part of the sky, the dome should move to accommodate that so the telescope can see out of it. But yep, there it goes back to its original position. Now, just a little side note, in case you were interested about this program, it is an accurate star map. So anywhere we touch on this sort of sky, or if we search for it in this little search box, is pretty accurate to what it would actually look like in the sky. You can actually see some constellations all throughout. Yeah, so this orange line is kind of a limit line. We try not to go below that line because it can damage the telescope if we're below it for too long. And this greenish line is actually the horizon. So we know we definitely can't go below that because we wouldn't see anything. So now that the telescope is where it needs to be, I am actually going to go ahead and open an image. So this was an image taken about a week ago on a really clear night. It was a pretty good night to take images. And this is our closest celestial neighbor, the moon. So some interesting facts about the moon. As I said, it's our closest astronomical neighbor in the entire universe. So if you think about the entire universe, the moon is the closest to us. It's actually not the largest moon in our solar system. It's actually the 5th largest moon in our solar system. Number 1 goes to a moon called Ganymede that orbits Jupiter. But the moon is actually only our moon is actually only a quarter of the size of the Earth. So it's also about 380,000 kilometers from Earth. So it would take a few days to get there and get back if we wanted to set up a travel program there, which I think NASA is thinking about going back to. I think there was something in the news about NASA planning a mission to go back to the moon, which would be pretty cool. A little bit more on kind of the structure of the moon. It actually has, if you think of the structure of the Earth, we have our crust, our mantle, inner core, outer core. The moon also has similar features. It has a solid iron inner core that is a lot cooler than the Earth's. And it has a liquid outer core and a very thick mantle, just like the Earth, except unlike the Earth, the moon's mantle is mostly solid, where the Earth's is mostly liquidy or viscous. And the crust of the moon is where all of the features that you see here. So when you look at it, you'll actually see darker spots that are called mare, and you'll see much lighter spots with a lot of craters. Those are called highlands. And this is actually the near side of the moon. if you look at the far side of the moon, there's actually, it looks all like all of the highlands. So it's very cratered and very, I think, and it's very thick crust, yes. So the near side of the moon has a thinner crust, while the far side of the moon actually has a much thicker crust. So on the topic of that, there is actually a theory called the giant impact hypothesis, thanks to isotopes found in moon rocks that were brought back with the Apollo missions. This hypothesis is that our moon actually formed as a result of a huge object impacting the Earth while it was still forming. And that impact really was a glancing blow that knocked a whole lot of material out of the Earth. And that material started orbiting the Earth and aggregated into our moon. And that's also what we believe created the geosynchronous orbit that allows us to only see one side of the moon throughout the year. So on that kind of topic there, as I mentioned, the near side of the moon is actually thinner and newer crust, especially the mare, while the far side of the moon is older crust. We actually think that's kind of a newish theory, that after that kind of collision, there was another collision that melted the near side of the moon and left the far side of the moon cool. But that's still an arguable theory. I'd also kind of like to touch on something that Dr. Kipping said, how we could possibly leave artifacts on the moon for future civilizations if we wanted to. So the moon does not have any tectonic activity like the Earth, and that's because the inside is so cool. But NASA actually has started a kind of preservation program or plan that they're starting to put together, because as we get closer to our realization of going back to the moon or going to Mars, we still have a lot of artifacts that are still there. So like the American flag that was put there in the 70s, the lunar rover, they're still there. A bunch of the rovers on Mars are still there. So fortunately, there are these measures being put in place to learn how can we preserve these spots, especially if space tourism becomes a big thing. But yeah, that is the moon. If you have any more questions about the moon, definitely drop it in the chat. I'm actually going to hand it back over to William, who's going to talk about some more interesting stuff.
Okay, thank you, Ashley. Great overview of the moon. So the next image we're going to show tonight is a galaxy. So if I just pull this up right here. So this beautiful image right here is called a Bodes Galaxy, BODE, Bodes Galaxy, otherwise known as M81 or Messier 81. And this guy was first discovered in 1774. It's 12 million light years away and has a diameter of about 90,000 light years. And for reference, the Milky Way is about 100,000 light years in diameter. So this is a relatively bright galaxy as far as bright galaxies and bright objects go, but you can't really see this without binoculars or a telescope. But because it is bright, it does make a good amateur astronomy target. So you can view it with a telescope or binoculars, and it's best viewed in the spring. So you could go outside and see this on a clear night tonight if you have some binoculars or a telescope. So a few things about this galaxy. The first thing we notice is that it has spiral arms kind of emanating and curling around the galaxy. So that's the reason we call or designate this a spiral galaxy, because of these very clear and distinct spiraling arms. And you'll notice that in some of these arms, we have slightly redder kinds of tints and splotches. And if you go on something like Google Images and you type in this galaxy, you'll get some images that have very bright pink splotches. And those are just regions of star formation. So in this particular galaxy, you have a lot of stars that are actively being formed in these spiral arms. So in the middle of the galaxy, we see something else. We see this very, very bright, compact area. So what is that? So that is actually called an active galactic nucleus, or an AGN. And an AGN is one of the most luminous objects in the universe. And we believe it's powered by accretion of matter, so gas and dust, onto a supermassive black hole. So in this particular galaxy, the supermassive black hole at its center is about 70 million solar masses, so 70 million times the mass of the sun. So that's an absolutely incredible amount of mass packed into a relatively tiny space. So you have a bunch of matter that is orbiting that black hole and occasionally falling in and getting sucked into the black hole. And you also have radiation being blasted out by that process as well. So that'll just light up this whole area and make it incredibly luminous. So that is Bodes Galaxy in a nutshell. And as a reminder, this is a colored and processed image. If we were to take a look at this live, we would more than likely not see, we certainly wouldn't see this level of detail in terms of colors and whatnot. We would probably be able to make out the spiral arms, and certainly we'd be able to tell that there's a brighter core at the center of the galaxy, but we probably wouldn't be able to, it wouldn't be as nice of an image as this. So at this point, we can turn it over to Kevin, who can talk about the research that we do at the observatory, which ties in quite nicely to the theme of Dr. Kipping's talk.
All right, thank you, William. Yes, like he just said, I'll talk a little about some of the research observing we do here at the JMU Observatory. Primarily, it is used for the detection of exoplanets, which is, yeah, very nicely themed. So how do we use our campus telescope to detect an exoplanet? They're obviously very small and very far away, and you can't really directly just take a picture of it, not with the resources that we have here. But what we can do is look at stars. So essentially what we are looking for is a transiting exoplanet. And what transiting means is that the planet in its orbit around its star will pass between its star and us looking through our telescope. And when the planet passes in front of its host star, it'll block a small portion of the star's light. And it's actually significant enough that we can measure it. And this is what that looks like. So essentially what we're doing is we are looking at a star for a long time, and we are measuring its brightness. And if we plot its different brightnesses over time, we can measure any dips that might be produced by a planet transiting in front of its star. And if we see those same dips of similar depths appear periodically, then we can infer that there is in fact a planet there. So this is an example. These plots are called light curves, and they're what we generate from the data we gather. This is of a confirmed exoplanet, and you can very clearly see these flat lines are light curves of other stars, and you can see they're flat. There's no planet transiting in front of them at this time. Whereas with the EXO 1b, you can see it's flat on the edges. And then as the planet starts passing in front of the star, the brightness decreases, and then it flattens out for a long time while it stays in front. And then as it leaves, the brightness goes back up to what it was before. I'll show a bit more clearer image just here so you can get a better idea of what it actually looks like when the planet's going in front and how that affects the brightness of the star. So our telescope does get used for research observing on most clear nights, and we work in conjunction with the TESS, the Transiting Exoplanet Survey Satellite NASA mission that helps identify which stars to look at. And then along with the network of many other ground-based observatories, we follow these up and try and determine whether or not those stars have planets. All right. I think that's about it. Again, if there are any questions about the observatory, anything you've seen, or anything about the research we do, just drop them down into the chat and we'll be happy to answer them. William, is there anything else?
No, I think that'll do it. So since the weather is kind of bad tonight, we'll just cut this tour short. So if you do have any questions, we'd be happy to stay around and answer them. So just type them into the chat. But otherwise, if there's nothing left or nothing else, I think that'll do it. So thank you all for joining us, and I hope you have a good night.
Oh, one moment. Sarah asked, how often do we use the telescope in person nowadays? Very rarely because of COVID. So it's actually, I believe, Kevin and I actually used it for one public night, about a month ago, I guess.
Oh yeah, that was us. We were there
Oh.
troubleshooting some hardware stuff.
Yeah, so outside of that, we haven't really been using the telescope in person. However, as Dr. Plavchan mentioned at the beginning of tonight, the governor has begun to relax restrictions on public gatherings. So we're hoping very much to be able to start using the telescope in person, definitely by fall. So, yes. So yeah, sorry, I didn't mean to step on your toes there, William. Just wanted to
Oh, that's fine.
ask that question. So yeah, everyone have a good night. Thank you for coming. Thank you for coming thank you for coming to this event. It's unfortunate that we did not have the weather so that you could actually we could see the telescope in operation and we could take active images of the current night sky. But I believe it's in the chat, someone had posted that the next time we have an event is April 14th. And so my experience is that weather tends to get better towards the summer months. So fingers crossed, hopefully we can have an actual viewing session on the 14th, virtually, of course, but hopefully we can actually open up the telescope for that. All right. Well, again, thank you all for coming, and I hope you all have a good night.